The most impressive construction projects on Earth happen in total silence. In clean rooms, where the air is filtered 1,000 times more than a hospital operating room. Here we build CPUs. I want you to reframe the modern computer not as a part, but as an immense, invisible construction project. We are talking about billions of transistors, each one a tiny switch manufactured at a scale so small that a single speck of dust looks like a mountain. These transistors are the building blocks of our digital age. But calling them components feels too sterile. Let's use a central metaphor that we can all grasp, the Lego masterpiece. Imagine a Lego set that doesn't have 1,000 pieces but 20 billion. And imagine that each piece is so small you could fit 500 of them inside a single human red blood cell. This is the scale of a modern processor. It is modular, precise, and utterly mind-boggling. When you click an icon on your screen, you aren't just running a program. You are triggering a choreographed dance across billions of these tiny Lego blocks. To understand the complex, we must start with the simple. Think of a single Lego brick. Specifically, think of that tiny circular bump on the top of the stud. On its own, a single Lego stud is almost useless. You can't build a castle with one stud. You can't even build a wall. But that stud is the fundamental unit of connection. It's the how of the building. In the world of silicon, a single transistor is that Lego stud. It is a simple switch. It's either on or it's off. Alone, it can't calculate your taxes or render a 3D video game. But when you combine these studs into groups, they form standard cells. Just as a 2x4 Lego brick is a standard unit used to build larger structures, a standard cell is a group of transistors working together to perform a specific task. This hierarchy is the secret to modern engineering. We don't design every one of the 20 billion transistors individually. That would take lifetimes. Instead, we design the bricks, standard cells, and then arrange them in patterns of unimaginable complexity. This is how we bridge the gap between a piece of sand, silicon, and a supercomputer. Let's look at the simplest brick in our Lego box, the inverter. In the world of logic, the inverter is the contrarian. If you give it a 1, high voltage, it spits out a 0, low voltage. If you give it a 0, it gives you a 1. It's the no person of the CPU. Why is this important? Because digital logic is built on contrast. If everything was just on, nothing would ever happen. We need the ability to flip states. The inverter is our first true look inside the processor's brain. It serves as the gateway to all other logic circuitry. Think of it like a simple light switch in your hallway that works in reverse. You flip it up, and the lights go off. It sounds trivial, but this simple act of inversion is the heartbeat of computation. It allows the computer to say, not this or, if not that, which is the foundation of every decision your computer makes, from, should I show a blue pixel, to, is the password correct? Now let's zoom in even further. We need to see the mechanics of the Lego stud. A transistor isn't just a symbol on a page. It's a physical object made of gates, channels, dielectrics, and metal contacts. To understand how it works, let's leave the world of electronics for a moment and go to your kitchen sink. Imagine a water faucet. You have the pipe where the water comes from, the source, the pipe where it goes, the drain, and the handle you turn, the gate. In a transistor, we don't use water. We use electrons. When you apply a tiny bit of voltage to the gate, it creates an electric field that opens a channel through the silicon. Suddenly, the electrons can flow from the source to the drain. If you take the voltage away, the channel closes and the flow stops. The dielectric is like the rubber seal in your faucet. It prevents the electricity from leaking out where it shouldn't. This is quantum scale behavior translated into intuitive mechanics. We are literally using a tiny electric handle to control the flow of the most fundamental particles in the universe. In nature, balance is everything. In computing, we achieve balance through complementary metal oxide semiconductor technology, or CMOS. This involves two types of transistors that act as mirror images of each other, N-type and P-type. Think of them like two different types of workers. The N-type worker is eager. He works when he's told yes, high voltage. The P-type worker is the opposite. He only works when he's told no, low voltage. By pairing them together, we create a push-pull mechanism. When one is active, the other is resting. This symmetry is what makes modern chips so reliable and energy efficient. Before CMOS, computers used to get incredibly hot because they were constantly drawing power. But with this mirrored pair, the circuit only uses significant energy when it's switching from one state to another. It's the ultimate teammate dynamic when one pushes, the other pulls, ensuring that the logic is always crisp, clear, and fast. Now, let's assemble our inverter circuit using our N-type and P-type workers. We connect the P-type to the power rail, the source of energy, and the N-type to the ground rail, where energy goes to rest. When you send a 0 signal to the gate, the P-type transistor turns on and connects the output to the power rail. Result? The output becomes a 1. When you send a 1 signal, the P-type turns off, and the N-type turns on, connecting the output to ground. Result? The output becomes a 0. We have successfully created logic out of physical materials. The abstraction of a 1 or a 0 is actually just the physical path that electrons are forced to take through buried layers of metal and silicon. It's like a train track where the switches are moved automatically by the train itself. This is the moment where physics becomes information. As humans, we can't always think in terms of transistors and electrons. Our brains would explode from the detail. So engineers use a shorthand to formal language of electrical engineering. We use logic symbols, like a triangle with a circle for an inverter, schematics, the maps, and truth tables, the logic rules. Think of this like a recipe. You don't need to know the chemical molecular structure of an egg to bake a cake. You just need to know that 1 egg plus heat equals structure. Truth tables are the recipes of the digital world. If input A is 1, and input B is 1, then output is 1. These symbols aren't just drawings. They are compressed representations of the physical reality we just discussed. They allow us to zoom out and design massive systems without getting lost in the microscopic weeds. It's the blueprints for our Lego cathedral. Once we have the inverter, we can start building bigger Lego bricks. By rearranging our N-type and P-type transistors, we can create NAND gates, NOR gates, AND-OR, XOR, and XNOR gates. Each of these is a slightly different decision maker. A NAND gate, for example, is the universal gate. You can build any other gate using only NAND gates. It's the Swiss Army knife of the CPU. This is where the Lego metaphor really shines. We've moved from a single stud to a 2x2 brick, then a 2x4 brick, and then a specialized window piece. By combining these gates, we can start to ask more complex questions. Instead of just, is this on? We can ask, are both of these on? Or, is either of these on but not both? This is the beginning of actual intelligence. The scale jumps again. We take hundreds or thousands of these logic gates and wire them together to form macrosals. This is where the CPU starts to actually do things we recognize. A macrosal might be an adder, which does addition, or a multiplier. At this level, we start to see higher metal layers. If the transistors are the basement and the ground floor, the metal layers are the elevators and highways that connect different parts of the building. Computation isn't just about logic. It's about routing and spatial organization. Imagine a city where everyone needs to talk to everyone else at the same time. You need massive highways, data buses, and complex interchanges to make sure the information gets where it needs to go without crashing. When you see a macrosal, you are seeing the architecture of mathematics itself, carved into stone, or rather, silicon. Now, we zoom out to the satellite view. Macrosals combine to form IP cores, things like the graphics core, the memory controller, or the arithmetic logic unit, ALU. These cores then combine to form the full processor. This is the peak of the Lego metaphor. At this distance, you can no longer see the individual studs, transistors. You can't even see the individual bricks, gates. You see a sprawling, magnificent castle. The individual pieces fade into insignificance compared to the astonishing complexity of the final creation. It's like looking at a human being. We are made of trillions of cells, but when you look at a friend, you see a face, not a collection of biology. A CPU is a digital person in that sense, an emergent entity that is far greater than the sum of its tiny switching parts. Let's pause. Neither a transistor nor a NAND gate is impressive on its own. A transistor is just a fancy rock that can hold a charge. A NAND gate is just a slightly fancier arrangement of those rocks. But together, assembled by decades of human engineering, they produce machines capable of painting digital masterpieces, connecting families across oceans, and simulating the birth of galaxies. This is the concept of emergence. Complexity doesn't come from magic, it comes from scale and structure. If you stack enough simple things in the right way, they become something intelligent. It's a humbling thought. Everything you've ever done on a computer, every like, every email, every game, is just the result of billions of tiny pieces of silicon saying yes or no in a perfectly timed sequence. Underneath the logic, there is a hidden backbone. Modern CPUs have dozens of metal layers stacked on top of the transistors. Think of it like a 15-story skyscraper where the ground floor is the office, the logic, and the other 14 floors are just wires and plumbing. There are kilometers of wiring in a space smaller than your fingernail. And then there's time. In our world, a second is fast. In the CPU's world, a second is an eternity. These gates switch in picoseconds, a trillionth of a second. Even massive, complex computations are resolved in a fraction of a nanosecond. Light itself only travels about 11 inches in a nanosecond. This means the CPU is working so fast that the speed of light is actually a bottleneck. The wiring has to be designed so that signals don't have to travel too far, because even at the speed of light, they might arrive late for the next clock cycle. It's a race against the fundamental limits of the universe. Why did we settle on CMOS? Why this specific way of building? It's because CMOS is the Goldilocks of technology. It has low power consumption, it doesn't leak much energy, high noise tolerance, it isn't easily confused by static, and safe voltage isolation. These principles are what allow your smartphone to stay in your pocket without burning a hole in your leg. It's what allows a supercomputer to process weather patterns without needing its own nuclear power plant. CMOS is the silent hero of the modern world. It's a design that prioritizes stability and efficiency, ensuring that whether you're in a freezing lab or a hot desert, your Lego castle of logic remains standing and functional. As amazing as this is, we are hitting a wall. We have made transistors so small down to 3 or 5 nanometers that we are running into the weird world of quantum mechanics. Electrons are starting to jump across barriers they shouldn't be able to cross, a phenomenon called quantum tunneling. We are moving toward multi-fin transistors, FinFETs, and even crazier designs where the gate surrounds the channel on all sides. The Lego pieces are becoming so small that they are starting to behave like ghosts. But this isn't the end. It's just the next chapter. Engineers are already looking at light-based computing, carbon nanotubes, and quantum processors. The journey of making things smaller and faster is far from over, but the challenges are getting harder, requiring more human effort than ever before. This story isn't just about silicon. It's about us. Behind every chip, there are thousands of engineers, decades of research, and billions of dollars in investment. Think about the explanation I've just given. It took dozens of script revisions, collaborative expertise, and hours of visualization just to make this understandable. Now, imagine the effort to actually build it. We use software called EDE, electronic design automation. That is itself one of the most complex pieces of code ever written just to help us place the transistors. We are humans using machines to build better machines to help us understand the world. It's a beautiful, recursive loop of intelligence. Understanding this complexity requires patience and clarity, but it also requires an appreciation for the sheer grit of the human spirit. As we reach the end of our journey, let's return to where we started. Modern civilization doesn't run on oil or gold or even money. It runs on vast, invisible networks of tiny switches, assembled with extraordinary care. What appears to be a seamless, magical digital experience is, at its core, a colossal Lego structure made of logic, metal, and time. We live in a world built on the no of an inverter and the yes of a power rail. We have taken the sand from the beach, refined it, and taught it how to think. It is a testament to what we can achieve when we break big problems down into tiny, modular pieces. When you look at a massive goal in your life, starting a business, learning a new language, or fixing a relationship can feel overwhelming, like looking at a finished CPU. But remember the Lego stud. Every massive achievement is just a series of standard cells. Don't try to build the processor today. Just focus on the inverter, master the smallest unit of your goal. If you want to write a book, don't think about 300 pages. Think about one sentence, one transistor. Then think about one paragraph, one logic gate. Eventually, the hierarchy of your effort will build something magnificent. Persistence is just the clock speed of the human soul. Keep switching, keep moving, and the macrocycles of your life will eventually take shape. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.